Hello everyone, welcome to this session. My name is Wycliffe, and in this video I want to share with you how you can monitor soil organic carbon in your field, in your forest, in your region of interest, wherever it is, near urban, away from urban region, wherever you want to assess soil organic carbon. I will give an example with the tea farm. We will look we'll assess soil organic carbon in several tea farms. So if you grow tea or you study tea or you simply love the science behind sustainable agriculture, this video is going to change the way you look at soil, because beneath every vibrant crop or plant or something like that lies a hidden powerhouse, which is the soil organic carbon, which is the key driver of soil fertility, root health, moisture retention, and ultimately yield of your crop and its quality. So soil organic carbon is one important aspect, parameter in the soil for healthy vegetation, healthy crops, healthy trees. But the challenge is that soil organic carbon is not something that we can spot with the naked eye, yet it varies dramatically across our fields. So today I'm going to show you how to map and quantify soil organic carbon at multiple tea fields using Google Earth Engine, and we will be able to do this in R, all with real satellite-based soil data from Open Land Map. So if you check Open Land Map, they have a soil organic carbon variable, or we can just check soil or just organic carbon. So we see this Open Land Map soil organic carbon content, and this is what we can use to assess the soil organic carbon at several depths, 0, 10, up to 200 centimeters. Yeah, so by the end of this video, you'll not only visualize soil organic carbon by depth across your sites, but also gain insights that can guide site-specific farm management, fertilizer planning, and long-term soil improvement. All right, so let's jump straight into the code and start building this soil organic carbon extraction workflow. Okay, so as usual, we start by loading the libraries which we use in building, in interacting with Google Earth Engine. So the main library is the rgee. We'll also draw some plots, which of course you may not need to do if you already have the shapefiles or GeoJSON or GeoPackage or vector data of your farms of interest, which you want to monitor. And then we will also use tidyverse to do some cleaning and SF to turn some Earth Engine objects to simple features. Okay, then after that, we initialize our rgee session. And if you are facing any problem with rgee, please go to the README file in my GitHub repository. You will find, if you go to my GitHub repository under rgee 30 days challenge, you will find a README file below, README file, which describes how you can set up your rgee, and you can then be able to use it in the extraction of data or interacting with Google Earth Engine. Okay, so after initializing, we will draw our sites. I will have I will monitor like 4 sites or 4 plots, draw features, and then this draw features comes from map edit. It helps us to draw features in interactively in a leaflet. Then we'll append each site a site ID identifier. For this, we'll just call them north, south, east, and west. The IDs can be anything, any ID identifier of your fields. Okay. Then after giving them the ID, then we only select that ID. Select site ID, and then we convert that SF as search engine object. All right, so where do we want to monitor soil organic carbon? As I said, I want us to do this within T fields. So I will zoom into areas where there are T fields. Yeah, we can monitor this in these big T farms. Okay, so I know there is T field here, there is T farm here, there is T farm here, and another one here. So let me just pick these major large T farms and draw some rectangles that are almost the same size. The rectangles I'm drawing may not be exactly the same size, and may not only cover the T fields, they stretch even into the forested areas. But this is for a demonstration. You can make them as accurate as possible as you wish. So those are my T fields. I think there are 4. They are basically of different areas, but you can make yours of the same size. Okay. So after having our 4 sites, then we can get the soil organic carbon data. So we can call it soil organic carbon, which is an Earth Engine image. And as an image, we then look for data set, and then we look for organic carbon. Yeah, open land map. Okay. So with that, we have loaded our open land map soil organic carbon. So to get the data, soil organic carbon data for our location, then we will take our soil organic carbon, then we reduce regions. We reduce regions because we have a feature collection, and the collection is called sites. It's where we have it's the 4 sites. Okay, then we use Earth Engine reducer, and we are reducing for the mean. That is, we need the mean soil organic carbon across those sites. And the scale of this data is 250. So you'll just use the native scale. Okay. So just like that, you have grabbed the mean soil organic carbon within the polygons. The next thing we can do is to convert this as an SF object. So we can say soil organic carbon SF is EE as SF. Okay. And then that is soc data. So that will convert the Earth Engine object to a simple features object, a very, very, very important function. For example, if we run this alone, we see that it is a feature collection. Soil organic carbon data is a feature collection because we have extracted it. But if we run SF, then we see everything that we want. We see the soil organic carbon data for each depth. The B1, B0, B10, B100 are the depths. So B200 is at depth 200 meters. And we have also the site IDs, which we selected when we were creating the Earth Engine sites feature collection. Okay, so we can convert this already to a data frame by saying as dot, not really as dot data frame, but soil organic carbon SF, and then ST drop geometry. So we do away with this geometry. We don't need it anymore. We only need this data frame up here. Okay. So we can proceed with our data frame, in which we will do some pivoting. So we will only have one column, and then the rest goes to, we'll only have it in the long format. So we can just say data frame gets the soil organic carbon data frame, and then we pass it to pivot longer. This is why we loaded the tidyverse, so that we get the tidy R. package to give us these functionalities. So the columns which we want to um, which we want to pivot are those that start with B. So the band B1, B0, B10, B200, B30, B60, these are the depths. So anything that starts with B, we want to pivot them. Then what will be the new names? The names of those bands, we can take them to depth because they are actually referring to depths. And then the values we take to, say, soil organic carbon or mean soil organic carbon, as you may wish. After that, or we can just run this and see how it looks like. We see that we now have the site ID. Then what we pivoted, or the columns we pivoted, are those that went to depth column. And then the values went to soil organic carbon. Okay, so after pivoting it like that, then we need to mutate these ones. The B1, B10, these ones are depths in centimeters. So we can mutate to better show them, or to show them better than just B something, B something. So we use mutate function from dplyr package, and in the mutate, what the column we want to mutate is the depth column. And then we say case when, that is when you find a place where in the column depth there is B0, okay? Assign that to what we want, maybe 0 centimeters. That is depth 0, the surface of the soil. But when you find that the depth is B10, then assign it a value of, say, 10 centimeters. I will just copy this because we are repeating this severally. If you find depth now to be 30, then assign it 30 centimeters. If you find that the depth is 60, then assign it 60 centimeters. You can just imagine somebody going to the farm with soil auger of different depths and digging at different depths, taking this soil into the lab and testing the soil for organic carbon. It's a very, very tedious process, and it's expensive process sometimes, and can take several weeks or months for somebody to get good results. But here we are extracting it in a split second, okay? So after setting all the depths accordingly, then we can convert these values to the right soil organic carbon values by dividing them by 5. If we look at soil organic carbon, probably that is something utils data set display. If we display the soil organic carbon data set, you will find under bands that we need to scale them by dividing them by 5. That is when we will convert them from into grams per kilogram, to convert them to grams per kilogram, the values we have. Okay. So when we get here, we can say this soil organic carbon we have, just make it soil organic carbon, but divide it by 5. So this makes it soil organic carbon in grams per kilogram. So we can arrange by site ID and depth so that we have our data set in the DF. So if we print DF alone, we now see the soil organic carbon in grams per kilogram of every site, the eastern site at different depths, the northern site for different depths, and until the last one. So we have done our extraction. If you wish, you can display this. So that will be ggplot. And then we pass the data frame, and then for the aesthetics, we can say X gets the site ID. And then on the y-axis, we have the soil organic carbon values. And then we fill the by depth. Okay. Then which geometry do we want to use? We can use Geomba for this, and we set start to identity. Then we can dodge the position so that the bars are separated. That's basically it. Yeah, so we see with this, we have the data frame itself, which you can convert to CSV and you can use it for whatever you want. And we can also make this kind of visualization where we see soil organic carbon at different depths. Generally, we see depth 0, a lot of soil organic carbon in the T fields at depth 0. What this basically means is that there is more soil organic carbon near the surface of tea farms. And this could be because tea farms are normally pruned every 4 or so years. And then the pruned materials are normally left in the farm. They are never taken away from the farm, so they decompose and add to the layer of organic matter in the soil, among other reasons. As we go to depth 200, depth 30, okay, depth 200, the color here shows very low soil organic carbon. So soil organic carbon is concentrated normally on the upper surface. Again, if comparing these 4 sites, my southern site appears to have less carbon in general compared to east and north and all that. Seems east at the highest soil organic carbon. But anyway, it all depends on the depth you are talking about and the management practices in different regions, soil organic carbon management processes that farmers apply in their farms. Some may remove the pruning materials, some may keep them in the soil. What I wanted to show is that you don't, sometimes, not always, sometimes you may not need to go to the lab and run tests on soil organic carbon. You can freely get this data as fast as you can see. We have obtained the data on soil organic carbon from a global database. Okay. And you can also map this. So map $ add layer. Soil organic carbon. That will be global, the whole world. And yeah, if you wish, you can assign it some good colors, as probably I will do in the version. Okay, thank you. If you find Okay, thank you. If you find this useful for you, you need some soil organic carbon to check on your farm, on your region, in your county, in your district, whichever. Please feel free to grab this code from the link I will leave in the description section of this video, and then try it yourself. Yeah, that's all I wanted to share for today. Thank you and happy coding. Bye-bye.